everyone. My name is Iza Sazanita and I am the instructor for this topic. Now let's start the lesson.
Digital Signal Processing, Chapter 3, Z Transform. In this topic, we will dive into a few subtopics. Number 1 is the definition of Z transform, number 2 is the region of convergence, number 3 is the stability and causality, and finally we will see a simple example of Z transform. Now, let's move further into the lesson outcome of this topic. At the end of this topic, the student should be able to give definition of Z transform, transform a discrete time signal to Z plane, and sketch region of convergence to identify stability and causality. Today, we will look at the use of the Z transform in analyzing linear time invariant systems. The Z transform is a powerful mathematical tool that allows us to study discrete time signals and systems more effectively. One of its main uses is to obtain the difference equation of a linear time invariant system, which is essential because it tells us how the system behaves in terms of input and output. This directly connects to evaluating the stability and causality of the system, two critical properties in system analysis. Now, why do we focus so much on the difference equation? The difference equation is not only the mathematical description of the system, but it is also crucial for implementation in hardware. It allows engineers to realize the system using digital components. What is Z transform? The Z transform is a mathematical tool used to analyze discrete time signals and systems. It works by transforming a signal from the time domain into the Z plane, which is a complex plane made up of real and imaginary parts. The forward Z transform takes a signal in the time domain and converts it into a new form called H-Z. This Z domain form makes the system easier to analyze, especially when we want to study stability or design filters. The inverse Z transform does the opposite. It takes Hz from the Z domain and brings it back into the original time sequence H-ant. So, in simple terms, the Z transform is like translating a signal into another language for easier analysis. Region of convergence defines the region in the Z plane where the Z transform of a signal converges to a finite value. Outside this region, the transform becomes infinite and is not valid. This concept is essential for determining important properties of systems. For example, region of convergence helps us check stability and causality. A system is stable if the region of convergence includes the unit circle. In practical applications like digital filters, signal processing, and control systems, understanding region of convergence ensures that system designs behave correctly and produce valid outputs. Now, let's look at the four conditions of the region of convergence. Condition 1. If a signal is 0 for all n, its Z transform is made of negative powers of Z. The ROC lies outside the outermost pole, beyond a certain circle in the Z plane. Condition 2. If a signal is 0 for all n, the region of convergence lies inside the innermost pole, closer to the origin of the Z plane. Condition 3. If a signal has values on both sides of ant, the region of convergence becomes a ring or annular region between two circles defined by the poles. Condition 4. If the signal is such that no region allows convergence, then the region of convergence is null. This means the Z transform does not exist for any value of Z. Let's talk about causality and how it affects the region of convergence. Causality determines how the region of convergence is shaped in an LTI system. Causality in the Z transform will determine the shape of region or convergence. In a causal system, the impulse response is 0 for all n value. So, in the Z plane, its region of convergence lies outside the outermost pole. In an anti-causal system, impulse response is 0 for value and more than 0. So, the region of convergence lies inside the innermost pole. In a non-causal system, the impulse response has values for both n values. Here, the region of convergence forms a ring between two poles. Stability is one of the most important properties in digital signal processing. In fact, it is even more critical than causality because a system must be stable to produce meaningful outputs. For a system to be stable, the unit circle must lie inside the region of convergence. In simple terms, all poles of the system must be located inside the unit circle. There are three possible region of convergence shapes: Number 1, exterior ROC is stable when alpha is less than 1. Number 2, interior ROC is stable when alpha is more than 1. Number 3 is ring ROC also stable when alpha is in the range of 1, and forming a ring around the unit circle. For example, in a digital filter, if the poles are outside the unit circle, the output will keep growing and never settle. If they are inside, the signal remains bounded and the system behaves properly. Let's look at a simple example of the Z transform. We are given a signal xk, and we want to find its Z transform. To solve this question, firstly, apply the Z transform equation, and substitute all the values of sequence k into the equation. Then calculate and simplify the calculation. This will give the Z transform of all number of sequences. Usually, the common Z transform pairs is provided or will be given in a table in the appendix. You may refer to past year's exam questions and you will notice the appendix at last page. Thank you for your attention. See you again in the next topic.